We like to tell ourselves a comforting story about the future, that one day we will look back at Earth the way sailors once looked back at a shrinking coastline, small, familiar, already becoming myth, and then we will keep going, past the moon, past Mars, past the last pale planets, out into the real darkness toward other suns. And, on paper, the story begins so well. In barely more than a human lifetime, we turned the sky from a ceiling into a doorway. We sent metal into orbit. We sent a human around the world in a single breath of history. We crossed the boundary of the atmosphere and learned brutally and beautifully that space does not forgive, but it does allow. The first satellite, Sputnik, rose in 1957 like a spark thrown into the cosmic night. 4 years later, Yuri Gagarin circled Earth and proved that a living mind could survive beyond the cradle. And in 1969, Apollo 11 pressed human footprints into lunar dust that had waited unbroken for billions of years. That moment did something to us. It rewired our sense of what impossible meant. Because if we could reach the moon, 3 days away, 250,000 miles across the void, then surely the rest was only a matter of time. Surely Mars was next, and then the outer worlds, and then the stars. A simple ladder of ambition, but the universe does not scale like our dreams do. It is one thing to step off a shore. It is another to cross an ocean that is not made of water but of emptiness so deep it becomes a kind of physics. The harsh truth is that everything we have achieved, every probe, every rover, every triumph has happened inside a tiny bubble, a neighborhood, our cosmic backyard. Even our most heroic messengers, the Voyager probes launched in 1977, are still moving outward like slow thoughts through an immeasurable mind. Voyager 1 has traveled more than 20 billion kilometers. Decades of motion, decades of silence, decades of cold sunlight thinning into nothing. And even now, that craft is not near another star. It is simply farther away from home than anything else we've ever built. This is the paradox at the heart of modern spaceflight. We have reached astonishing distances, and yet we have barely gone anywhere at all. Because the stars are not the next country over. They are not even the next planet. They are not far in the way we normally mean it. They are far in a way that breaks intuition. Far in a way that turns time into a barrier and energy into a currency we don't possess. So, when people ask, why can't we just go, why can't we do for the stars what we did for the moon? The honest answer is unsettling. Not because we lack courage, not because we lack imagination, but because between here and the nearest sun is a distance so immense that our greatest machines moving at their greatest speeds become almost still. And the moment you truly feel that, really feel it, you understand what interstellar space is. Not a destination, a verdict. To understand why the stars still won't let us go, you have to zoom out until the numbers stop behaving like numbers. Distance in space isn't just more of what we already know. It's a different category of separation, one so extreme that it changes what a journey even means. Start with what feels familiar, the Earth and the Sunday. On the cosmic map, that distance is our first unit of intuition, about 150 million kilometers, one astronomical unit. It's enormous by human standards, yet in the language of the universe, it's almost nothing. Sunlight crosses it in a little over 8 minutes. A signal, a thought, a flash of radio gone before you finish a sentence. But even inside this small-scale time, already starts to stretch. When Voyager 1 left Earth, it didn't simply fly outward into a straight line of emptiness. It navigated gravity wells-made slingshot turns, crossed the orbits of worlds that are themselves separated by distances that dwarf our imagination. And after more than 40 years, it reached the outskirts of the sun's influence, approaching the boundary where solar wind fades and interstellar space begins. Not because the spacecraft is slow by engineering standards. 17 kilometers per second is fast. It's because the arena is obscene. Now widen the lens one more step. Look up at the nearest star, Proxima Centauri. It is not a distant glitter on the dome of the night. It is a real sun with real gravity, real worlds, real history burning in its core. And it sits 4.24 light-years away. That phrase, light year, sounds poetic, but it is brutally literal. The distance light travels in 1 year, about 9.46 trillion kilometers. Multiply that by 4.24, and you are no longer talking about a trip. You are talking about a gulf. If we launched a spacecraft today, and it traveled at Voyager's speed, the math becomes almost insulting. Roughly 70,000 years. Civilizations rise and vanish in a fraction of that. Languages mutate beyond recognition. Continents reshape. Even species can disappear. A ship launched at the dawn of agriculture would still be on its way. So, the first wall we hit is simple. The universe is too big for the kind of speed we currently know how to achieve. And you might say, fine. Then go faster. Build a better engine. Strap on more fuel. Turn the dial up. But physics is waiting there, patient and uncompromising. Speed is not a linear problem. Each small step closer to the speed of light demands a larger and larger payment in energy. The faster you push, the more the universe resists you, not through malice, but through the structure of reality itself. At low speeds, a little more fuel gets you a little more velocity. But as you climb, the cost starts to explode. Eventually, the energy required becomes less like engineering and more like astronomy. This is why the distance problem is not just about miles or kilometers. It is about time scales, energy scales, and the terrifying realization that there may be no practical in-between. Either you crawl through interstellar space over thousands of years, or you attempt speeds so extreme that your ship begins to resemble a moving power plant, a weapon, a star in miniature. So yes, space is vast. But the deeper truth is harsher distance is the first obstacle, and it drags every other obstacle into the light behind it. Propulsion, power, survival, even the meaning of going home. Because once the nearest star is measured in years of light, the question stops being, how do we get there? And becomes, what kind of civilization could even afford the journey? Type continue to write chapter 3. We tend to imagine propulsion as a simple ladder, the Wright brothers, to jet engines, to rockets, to something faster still, as if speed is just a matter of iteration, one breakthrough after another, until eventually we're cruising between stars the way planes cross oceans. But propulsion in space isn't an ordinary engineering problem. It's a negotiation with the deepest rules of motion, and the universe drives a hard bargain. The fastest human-made object in deep space is not a sleek starship. It is a small, patient machine built for endurance. Voyager 1 moves at about 17 kilometers per second, fast enough to circle Earth in under 40 minutes. By terrestrial standards, it is an arrow. By interstellar standards, it is drifting. The reason is simple and cruel. Every engine we have ever flown obeys a constraint that becomes deadly at large distances. To move forward, you must throw something backward. That something is reaction mass propellant. And once you leave Earth, you cannot refuel at a gas station. You must carry your entire future in your tanks. Chemical rockets are the brute force solution. They deliver enormous thrust in a short time, which is why we can launch from Earth at all. Hydrogen and oxygen ignited into expanding gas, pushing against the nozzle, pushing the craft upward. It's violent, it's elegant, and it's fundamentally unsuited to interstellar travel because chemical energy is small compared to the energies locked inside atoms and nuclei. To keep accelerating for months, years, decades, you would need absurd amounts of fuel, so much that the ship becomes mostly propellant, hauling propellant to haul propellant, an exponential prison of mass. So we look for efficiency. Ion drives, for instance, feel like a glimpse of the future. Instead of exploding chemistry, they use electricity to accelerate charged ions out the back at incredible speeds. The exhaust is thin, ghostly, almost nothing, but the efficiency is beautiful. Missions like NASA's Dawn used ion propulsion to visit and orbit distant bodies in the asteroid belt, proving that slow, continuous thrust can reshape what's possible in the solar system. And yet that word slow returns like gravity. Ion engines sip fuel, but they push gently. Their acceleration is measured not in roaring power, but in patience. Given enough time, they can build up speed. But interstellar travel does not offer enough time, unless you're willing to think in decades just to reach a fraction of what the stars demand. So naturally, our minds leap to the fire that powers the universe itself, fusion. Fusion is the dream engine, the same process that turns hydrogen into sunlight inside the core of a star. In theory, a fusion-powered craft could achieve velocities that begin to make the light year feel less like a wall. You can already hear the promise in the language fraction of the speed of light. Not 1%, not 5. Something meaningful. But theory is not a ship. We have not yet mastered sustained practical fusion even on Earth, where we can build massive reactors and surround them with infrastructure. A starship would require fusion made compact, reliable, controllable, and safe, operating for years in deep space, far from repair, far from rescue. It is not one invention. It is an entire industrial revolution condensed into a machine that must never fail. And beyond fusion, the ideas become stranger, almost mythic. Solar sails, thin mirrors, catching light itself as thrust. Laser propulsion, where Earth becomes the engine, firing a beam at a reflective sail to accelerate a probe outward without it carrying fuel. Breakthrough Starshot is one such concept, a fleet of tiny craft pushed by powerful lasers, potentially reaching around 20% of light speed. 20%. Suddenly, Proxima Centauri isn't 70,000 years away. It's a few decades. But every gift from physics comes with a hidden cost. A sail pushed that fast becomes a target. A speck of dust becomes a bullet. A stray atom becomes an impact. And then comes the most unforgiving problem of all arrival. How do you stop? Acceleration is hard. Deceleration is harder. Without an engine on board capable of braking, a probe would arrive at another star, like a stone, fired past a campfire, blazing through the system in hours or days gone before it can truly look, study, or touch. It wouldn't be exploration. It would be a flyby at relativistic speed, a cosmic glance that costs a civilization-scale effort. This is the escalation. It's not enough to go fast. You must go fast safely. You must carry power, protection, navigation, communication, and the ability to slow down, all while crossing distances that make every failure permanent. So, propulsion is not merely the question of, can we build a faster engine? It is the question of whether the laws of physics allow a machine to be both fast and survivable across an ocean that turns time into an enemy. Type continue to write chapter 4. Time is the invisible wall, the final layer of the trap. Because when you stretch a journey across light years, you don't just ask how far, you ask how long. Must reality continue to cooperate? How long must the ship endure? How long must a civilization remain stable enough to support it? How long must the travelers remain human biologically, psychologically, culturally, before the destination arrives? At first, the solutions sound like engineering, but they quickly become philosophy. One idea is the generation ship, a vast, self-sufficient habitat, traveling for centuries, where the original crew will never see the target star. They would die en route, and their descendants born into corridors and artificial skies would inherit the mission like a religion. On paper, it solves the time problem. In practice, it opens a darker one. Because a generation ship is not a vehicle, it is a society, and societies are fragile. Systems must last longer than any technology we've ever maintained. Food production, recycling medicine, governance, education, everything must persist across centuries without outside help. A single cascading failure is not an accident. It is extinction. And then comes the ethical wait consent. The first generation chooses to leave, but every generation after is born into the voyage without being asked. Their entire universe is a ship they didn't choose, moving toward a world they've never seen for reasons that may no longer feel meaningful. What happens when the mission becomes inconvenient? When belief fades? When the descendants decide that arrival is not worth the sacrifice? A generation ship is a solution that depends on something physics cannot guarantee the continuity of. Purpose. So we reach for a different fantasy hibernation. Cryogenic sleep. A crew that leaves Earth, closes their eyes, and wakes at another sun with the same faces, the same names, the same memories of home. It is a beautiful idea because it restores the human scale. It lets a multi-decade voyage feel like a night, but right now it is still science fiction. We do not have a safe, reliable way to slow human biology to a halt and bring it back without damage. Not for years, not for decades. And certainly not for the kind of deep time journeys that make the stars truly accessible. So the mind goes further into the realm of space-time itself. Wormholes, warp drives, shortcuts through the fabric of the universe. These concepts are not mere imagination, they exist in the mathematics of general relativity. But mathematics is not a promise. A wormhole, if it could exist, would need exotic conditions we have never observed or controlled. A warp drive in the forms we describe demands forms of energy that may not be physically realizable. These are not technologies waiting to be built. They are ideas waiting to be proven possible. And while we wait, relativity offers its own strange compromise: time dilation. Einstein showed us that time is not absolute. It stretches and compresses depending on speed and gravity. If you travel near the speed of light, time passes more slowly for you than it does for those you leave behind. In theory, a crew could cross interstellar distances while experiencing far less time than Earth does. From their perspective, the trip might take years. Back home, decades or centuries could pass. It sounds like salvation until you look at what it really means. Relativity does not let you cheat time. It lets you trade it. The travelers keep their years, but Earth pays the bill. When the ship returns, or even if it simply sends a message, it returns to a world that has moved beyond it. Everyone they loved is gone. Every institution that launched them is history. Their departure becomes a date in a museum. And this is the deeper, colder implication. Even if we master near-light travel, we may lose what we thought interstellar travel was for. Because an interstellar civilization, the kind we see in fiction, trade routes between stars, political unions across sectors, a living web of worlds, requires something relativity, denies fast, meaningful interaction. The faster you travel, the more you separate your timeline from everyone else's. Your ship becomes its own drifting era, disconnected from the home that built it. So you begin to see the real shape of the future. Not fleets and empires, not highways between suns, but islands. Each ship, each colony, each civilization becomes an island of consciousness in a sea that will not carry messages quickly enough to hold a single culture together. Even if we reach the stars, we may not reach them as one people. We may fragment into lonely worlds, each one evolving in isolation, cut off not by malice, but by the speed limit of reality. And in that loneliness, an ancient question begins to sharpen into focus. If the universe is so old, so vast, so full of potential, why don't we see anyone else? That question has haunted astronomy like a shadow behind the stars. Fermi's paradox: if the universe is so big and so old and life seems possible in so many places, then where is everyone? For decades we've imagined grand answers. Civilizations that rise and fall, galactic empires, beacons and wars and hidden worlds. But sometimes the most unsettling answer is the simplest mirror. Look at us. We are a species that has cracked the atom, mapped the cosmic microwave background, built machines that can see galaxies at the edge of time, and yet we are still trapped inside the same small bubble of space our ancestors saw as gods. We have stepped onto another world, yes. We have scattered robots across the dust of Mars, yes. We have thrown probes into the outer dark, yes. But even now, our farthest travelers are closer to the sun than they are to any other star by an absurd, humiliating margin. And that may be the point, because perhaps the universe is not empty of life. Perhaps it is full of it, full of sparks that ignite on countless worlds across billions of years. But if interstellar travel is as brutal as the physics suggests, then each spark becomes a lantern surrounded by an ocean it cannot cross. The distances are not merely inconvenient. They are isolating. They enforce separation, the way oceans once enforced separation between continents. Except these oceans are made of vacuum and time, and the waves are measured in years of light. Consider the timeline. The universe is about 13.8 billion years old. A sun-like star can shine for tens of billions. Planets form early. Life, if it begins at all, may take billions of years to crawl from chemistry to cells to minds. If that process is common, then many civilizations could have emerged long before us. They could have had entire eras to advance. So why haven't they arrived? One answer is that arriving might not be a real option, not in the way our stories assume. No warp gates, no convenient wormholes, no casual hopping between stars like stepping stones. Just propulsion that demands impossible energy survivability, that demands a sealed world for decades or centuries, and time itself acting as a blade that cuts travelers away from their origin. In that framework, the galaxy could be full of intelligence and still appear silent. Because each civilization is locked to its local neighborhood, able to explore its own planets, perhaps able to seed a few nearby stars if it is patient, if it is willing to accept journeys measured in lifetimes, but unable to spread rapidly, unable to weave the galaxy into a single connected web. The universe doesn't need to kill civilizations to hide them. It only needs to separate them so completely that they never meet. And when you truly accept that the cosmos changes shape in your mind, the night sky stops being a frontier waiting for conquest and becomes something stranger, a scattering of distant shores, each one possibly lit by minds that will never touch ours. Not because they don't exist, not because they don't look, but because the gulf between stars is not a gap, it's a regime of physics that turns contact into a near impossibility. So what does that mean for us? It means our dream of leaving may need to evolve. The solar system is not small. It is a vast kingdom of worlds, moons, oceans, under ice, deserts of rock, and methane haze, rings and storms, and silent comets carrying ancient chemistry. Even exploring it deeply, truly deeply, could take centuries of careful work. And perhaps that is the kind of exploration the universe actually allows: depth over distance, mastery over imagination. But the dream doesn't die. It changes tone. Because even if interstellar travel remains beyond us for a very long time, the urge behind it is real. We look outward not only to escape, but to understand what we are. We build probes and telescopes and theories because we cannot stand to be confined to a single world in our minds, even if our bodies must be. And maybe that is the final lesson, hidden inside the stars, that the universe is not obliged to be reachable. It does not owe us an easy road. It offers beauty, terror, and scale so immense it induces vertigo, and then it asks a quiet question back. If the cosmos is too vast to cross, what will you do with the small, precious corner you can touch? Once you accept the true map of the journey, the next realization arrives like vertigo. Mars is not difficult because it is far in the way the moon is far. Mars is difficult because it is far in time, and time and space is a tax you pay en masse. The closest approach between Earth and Mars is a rare moment of mercy, a window that opens only when the planets align in a favorable geometry. Roughly every 26 months, the solar system briefly arranges itself so a crew can ride an efficient arc, an interplanetary shortcut carved by orbital mechanics. That window is everything, because the moment you miss it, the trip doesn't become a bit longer. It becomes fundamentally different. You need more energy to intercept Mars, more propellant to break into arrival, more propellant to leave, and often far more time. And every extra day in transit is another day you must keep human beings alive inside a sealed machine. This is the escalation that people underestimate. Mars is a mission you don't just launch. You assemble, you stack. You build it in pieces because no single rocket, no matter how powerful, can easily lift an entire self-sufficient world into orbit in one clean strike. Life support systems, habitats, radiation shielding, food stores, spare parts, propulsion stages, landing vehicles. Each element adds weight, and weight is the master variable of the entire equation. If you want more safety, you add redundancy. If you add redundancy, you add mass. If you add mass, you need more propellant. If you carry more propellant, you need a bigger vehicle to carry that propellant. And the spiral continues, a feedback loop of engineering reality. We've seen this progression before in miniature. Early human flights around Earth carried a single person and a capsule barely heavier than a car. Lunar missions demanded vehicles tens of times heavier launched by rockets that were closer to skyscrapers than machines. Mars pushes beyond that again because it stretches the mission from days into years. A lunar mission can survive on minimal supplies because it is short. A Mars mission is not short. A plausible round trip can require many months to get there, a long stay to wait for the next return window, and many months to come home, approaching 1,000 days of continuous life support. That duration changes the nature of risk. In low Earth orbit, A failure can be answered with a replacement. On the International Space Station, a broken pump, a failing component, a medical emergency, there is at least the possibility of rapid response. On a Mars trajectory, a broken pump is a potential death sentence. You cannot send a part fast enough to matter. You cannot send a rescue crew that will arrive in time. So the spacecraft must carry the solution to problems that haven't happened yet. It must be designed like a lifeboat that cannot see land for years. Then comes the most unforgiving requirement of all propellant. In orbit, you are always negotiating with momentum. To go to Mars, you must accelerate out of Earth's grip, shape your path around the Sun, and later cancel that enormous interplanetary speed to arrive safely. Every major change in velocity costs fuel, and fuel is mass, and mass is the enemy of launch. Estimates for a human Mars mission often reach into the hundreds of tons of propellant for the full architecture, sometimes approaching a scale comparable to or exceeding the mass of entire space stations. So the obstacle is not a single wall, it's a cascade. The distance forces a long duration. The long duration forces more supplies, more shielding, more redundancy. That forces more mass. More mass demands more launches, more assembly, more complexity. More complexity creates more failure points, requiring even more redundancy. And around the loop tightens until Mars stops looking like a destination and starts looking like the ultimate test of whether our species can build a self-contained ecosystem that remains stable while it falls through the time void. Mars is not a place you simply go. Mars is a place you earn by defeating the compounding mathematics of survival.